First of all, hi, my name is Konstantinos Servis, Costa for short. I am kind of new to the HPC space, but I have experience. So most of my experience is from data engineering in web analytics, where we use things like Hadoop. Okay?
Wait, just a second.
And
no, it's yeah. The mic is the mics are those ones. So someone is saying that the audio is not optimal, but yeah, the mics are those two. So it should be fine. No, there's nothing.
No, can
Yeah.
you sit over because that way we can see Costa as it's speaking.
So, can you hear me now? Someone from the chat, please.
No, this is just for the camera. This is just for the camera.
Someone online. Can you hear Costa speaking now?
Can you hear me? 1, 2, sound test. Yes, good.
Yeah.
Thank you.
So
thank you. All right. So yes. So my background is from web analytics. What's called data engineering. There we use things. So I'm not going to go into that too much, but we use a thing. We used to use a thing called MapReduce, and based on that, we have done many nice things in an ecosystem called Hadoop. And I have a lot of experience in that, and it's a wonderful thing. So 2 years ago, just to give a bit of context, I came here, I thought this is amazing. I'm going to start working on looking at other planets, craters and things like that. And I didn't find any of the tools that I need. So I went totally old school and started writing scripts for everything that was needed, and proceeded to make a mess, which was a useful mess. But I am happy to say that we found Nextflow at the end after some iterations, which can help in some ways. I'm hoping to convince you of that. The one reason for anyone who may have heard of this concept, one reason I like Nextflow so much is because it maps conceptually really well to MapReduce. That's for anyone who may have heard this term before. So what's the purpose and the structure of Cda? So what we do is, Cda is the crater detection algorithm. What we do here is we pretty much, not going to the scientific case, we count craters for planetary science. At the core of the technique is, as I said, crater counting. One can simply start manually marking craters, and some people in this room have done it, and it's tedious. That is a very slow task. If we use object detection and a convolutional neural network, which we do in this current version, and we use YOLO v3, we can do this in milliseconds. So for a single scene, as I'm mentioning here, which can contain hundreds of craters, we can literally score this or produce detections in milliseconds. This problem is also trivially parallelizable, so we can process the entire surface of Mars down to a crater size of, for instance, 5 meters per pixel in 24 hours, producing 94 million craters in an HPC cluster, or thereabouts. There are several high-level tasks that are coded as workflows within Cda. We have georeferencing. What we call georeferencing is obtaining a raw orbiter image and producing image that contains spatial reference system. We need to do our training. We need to which involves using the labels that somebody manually and tediously and very slowly has produced to train the network. And we also perform inference. Inference in this case is referring to obtaining an image and producing a list of where the craters are in geographical coordinates and how large they are. And finally, another thing we do, and it's very useful, we call it annotation. So basically, we take the same image and the produced output, and we make it nice and viewable so that we can verify our results, although the analysis is performed in a different way. All right, so here's the inference workflow that I mentioned. So for each of our scenes, and a scene in this case is an image, an original high resolution image from a planetary body. In this case, well, I will be using Mars. So imagine we have a box of 1 by 1, let's say, degrees of latitude and longitude. That would be a scene. That would be a high resolution geotiff. We would use GDAL. Some of you may know that, to downsample the image. So downsample in this case, we would be going from 5 meters per pixel to 40 meters per pixel, 160 meters per pixel. So pretty much we are mapping 4 pixels into 1. The reason we do that is so that we can also detect larger images as we stride over. For those of you that may have heard object detection before, as we stride over the image, the stride or the window that we look at is may not contain the larger craters, will not contain the larger craters. So we need to downsample to do that. Finally, we go into, for each of those images, the lower resolutions that we have downsampled and the original ones, we have to tile them. So we produce standard tiles. This is configurable in our workflow. The tiles are 960 by 960 pixel JPEG tiles. So we've left the world of geographical coordinates. Then we use YOLO v3 to do the object detection. So we have some object detections that actually don't make much sense not even for the original image, and we need to untile those. So by untiling, in this case, we are referring to the pixel coordinates in the original image. We have like a convention for doing this. We end up with the object detections for the image. So this is a file finally that will be in geographical coordinates and will tell us in these geographical coordinates, you have a crater and the diameter is X. And finally, because we have multiple images, sometimes we will get duplicate detections. For these duplicate detections, we need to find out which one is best. We will define an overlap for what is a duplicate. So we will say when the intersection over union ratio is in some number, 0.3 in this case, I think we use by standard, we will consider the duplicate and only keep the one that has maximum confidence. That's where the term non-max suppression goes to. And finally, so we have object detections for scene which are not duplicates. So this is an example inference execution for the crater detection. So we have 15,000 approximately. So these are approximate numbers. 15,000 original size images. They are 5 meters per pixel from Mari Lab. We get them onto our system by using Zeus copy queue. We downsample each to 40 meters per pixel and 160 meters per pixel. We end up with 45,000 images. So the downsampling happens on Magnus work queue. Tiling, we end up with a few tens of millions of tiles. We score each tile by scoring. We get a detection. We do it in GPU queue on Zeus or Topaz. We need a GPU for this. We untile each group back to work queue on Magnus. We run the non-max suppression that I mentioned before on groups of 9 adjacent scenes. Considerations. Executions do fail. For anybody who has heard before about distributed systems, you're guaranteed to have failures, even if it's a failure that is not related to your code. And we can talk about this some other time. But execution needs to be done in groups. Otherwise, if we spawn millions of jobs on Slurm will not be able to handle it. But we need to be able to identify groups so that we can individually repeat them and debug them. And finally, another consideration is that we need the dev and test to happen on local Docker. So on my laptop, I would like to be working on my laptop and do the same thing with maybe changing one switch or one configuration on Slurm and on our clusters. I only have 8 minutes. So this is the bash version. I'm going to briefly talk about what I did here. Actually, I just have 4 levels of scripts. The point here is that there was a lot of repetition So I could go and show you some of the repetition and some of the horrible things, but I have witnesses in the room that can testify that it's write-only code. I can show you one script as an example. This is what we are doing. So we have a number of batches. We schedule a number of inference batches. We schedule the NMS run at the end. We use the Slurm dependency, and I'm not going to go into too much. But anyway, trust me. Yes.
You can, if you run over a little bit, that's fine, because the recording will be available for everyone. If
Okay.
they need to leave, it's okay.
All right. Okay. So in which case, maybe I'll show you one of the scripts. So if we look at the batch. Okay. Right. Can anyone from the chat? Can everyone from the chat see this?
Maybe one or two notches up.
Maybe.
Yes.
All right. Yeah, you can see it.
Okay.
Cool. All right. Thank you. So the batch inference run. In this case, here's the horrible hacky things I'm talking about. So I'm pretty much using Perl in order to hash the name and turn it into a specific bucket that I can always identify as a specific bucket. Then I go into another layer of scripts that's called inference run. And for this, I need to tile the image, detect the image, do the detection, the actual detection, untile the image, like I was saying before. Yes, you can see it. I'll show an example of one of the leaf or end images. So exactly like we were seeing before on Nextflow, here's the image. I call it a Docker image. I'm using a fact that Singularity can read Docker images. So here's the Docker image like we were doing before. Here's a horrible thing to turn it into a name that will actually work on a file system, and I will pull it if it's not there. It's horrible. Right. I hope there's enough evidence that we need some improvement. So let's go into how it looks now using Nextflow. Now, here's the beautiful thing. Nextflow, on top of having a kind of easy direct mapping from conceptually from MapReduce processing onto processes and channels, we have extra tools such as the execution graph. We can see what our graph of executions look like. This is a tiny image. I'll show you a better one later, so don't worry about this too much. We have resource usage graphs, and we have a timeline, so we can go in really. We have fantastic tools for finding out if we have done something wrong in the way we have created our execution graph. If there is a hog, like a resource hog, if there is something that's taking forever. So I'm going to actually show you the code. So this is the Cda code that I'm going to talk about. All right. So before I actually show you the code, I'm going to go ahead and run it so we don't have to wait for it. It only takes 3 minutes for a single image, but I'm just going to start it so we don't have to wait for it. So work and results, I'm going to get rid of them because this is where we keep our intermediate, and you're not going to see the execution actually. So this is it. So basically, I'm running something very similar to what Marco showed before, but you recognize things like profile. So I'm using a Docker profile. I also have a Slurm profile. I have an entry point. I'll show you what that is. I have an input image. This is a Marilab CTX mosaic. It's an image from Mars. This is the tile size. As I said, it's configurable. This is the weight. These are the weights. The weights are referring to what the neural network, the trained neural network, actually uses to make the detection. The planetary body is Mars. We need to specify that for part of the process, and the resolutions list for downsampling, 40 meter and 160 meter, like I said. And the non-max suppression output file finally is this. This final argument produces a report, and we will be looking at this report. So I'm going to start it and make sure that it has started. Okay, it has started, so it will do its thing. And I am going to go ahead and show you some of the code. So this is the inference run. As I mentioned, we entered the entry to this is a separate images with downsample. Now, if you recall a little bit our use case, we have some input images. So we've created a channel of input images, and high level, airy, fairy. We are downsampling this. We don't know what this is, but we can see what we need to do is downsample and then use another workflow, which we call overlapping images. So if an image is overlapping, like I was saying before, it produces duplicates. We need to run it with an NMS. So what is really cool here, and what we can focus on this, is that we can reuse another workflow, which is right above. We can use another workflow that is for overlapping images. But in this case, we want to have a downsample step before. They are very similar, so there's no reason to duplicate. It's beautiful that we can reuse code in such a way. So this is, there are two ways of writing workflows. This is one of them. You can directly run this. Probably you can also, I don't know enough, but you can probably also run this directly somehow in the command line, but
yes,
you can also run that.
There's a syntax.
Yeah, there is. So, but what you do is here, you specify input very similar to a process. You have an input file, separate images with inference is one step, non-max suppression is the other step, and you have the output. Okay, you can say, Costa, that's fantastic. These are just words that you've, they don't mean anything. So actually, the cool thing is that I've separated out my individual processes, so into a library. I call this Cda library. I'm going to show it to you as well. So this is the Cda library. So I'm going to show one of these steps, not all the steps. So this is core tiles using YOLO v3. So I have a number of inputs. I have the actual file. I have each, meaning I want to, for each process to have the config directory. I have for each process, I want to have the weights file. And finally, I need the path that I need to move around that contains the actual tiles, which came from a previous step. So in this case, I'm just using Python. I'm just using the one script in there that's called detect, a number of arguments, and I'm saving all in a CSV directory. Now, I have, if you can see here, I've mentioned nowhere the fact that whether I'm running on Docker or I'm on Slurm. So one thing I really like about Nextflow, and I know I sound like a salesman, but I actually enjoy it a lot. So here are my profiles. So in config, I have specified that I would like to have a Pawsey, I call it Pawsey, actually not Slurm, and a Docker profile. The Docker profile, let's have a look at the Docker profile. So here's the Docker profile. I can go in and say, for this thing that I was just showed you before, score tiles YV3, I want to use this particular container. I want these container options. I wanted to use GPUs, all of them, but I only wanted to fork once because I ran out of memory. So I wanted to only have one parallel execution of this. I mean, this is too much for my GPU. Great. So, and that works perfectly. If I need to do the same on Pawsey, I have a completely different way of doing that. I need different container options. I still do use the same container, but could have used another one. I don't know if that would make sense, but I could have used another one. And I'm saying just pick it up from Docker Hub. I run it on Topaz. Here is so the fact that I need to use GPU, the queue that I want to use, Slurm, everything is there. It's beautiful. And I enable Singularity for all of them. So here it is. So what I wanted to show you with that is that just by using different configurations that don't get into the actual process, I can run it on all the target platforms. I think this is a very powerful feature. So here's my output. So I have, like I was saying, I asked here the program to produce some output for me. So here's results. Marilab, what's it called, NMS CSV. So it's here. It contains things. Let's, I mean, most mortals would not be able to visualize this in their head. So let's do an annotation. Let's do an annotation run. So that's just done. Excellent. So this produced an annotated image that I have requested, and here it is. Beautiful map of Mars with our little craters, and when we zoom in, we can see that there is a. It also tells us what is the size of each. Some of them are not real craters. I mean, I don't know. There is an expert in the room, but I would say that this is not a crater. This is a crater. Most of them are craters, so we know for a fact from some verification it works really well for our use case and have produced some very interesting results. So, yep, this is the annotation. So I did run it for a single image like I promised, and I did use the annotation. That was for a single image. You can imagine that we can multiply that time that it took me to do that for multiple images. But cool thing is it's trivially parallelizable. You just have to spawn a lot of parallel tasks for an individual input file. So the Nextflow version of Cda. So the advantages are too many to enumerate, but here are some. We have modularity, like you saw, reusability, configuration injection, readability. I mean, this, if you compare what I wrote here as code, this is a language called Groovy. It's a kind of a Java scripting language. And it's much more readable than, if I show you this thing.
It just still look like bash scripts, but in a more organized way.
That's the thing. It's a structure.
Well, so the other thing is that I wanted to get some result from this. And I always had it in my mind that this is horrible and I can go and refactor it, but I never have the time to go and refactor it because that's not my main job. And this is a common pattern, and it's a beginner mistake, and I did it. But it's actually a very, and when you do a cost-benefit analysis of your time, it happens a lot. So more target platforms. So I have all more target platforms for free with a lot less code. I have my visualization, which I want to show you before I close. I want to show you the report as one of the outputs. Here's the Nextflow report. This is the thing that we just ran. The report is already there. It's telling me what was the CPU usage from the different steps. This is the memory that each step is using. This is the job duration. This is the I/O. You have a ton of input stuff, of interesting things to look at. Yep.
There are also two other types of graphical reports. One is the timeline, which really shows you in a project management style what were the task dependencies and how they ran over time. And there's also the possibility to build the DAG,
correct. So I have
graph of all tasks.
So I have these actually. I have
and this comes from free. Just enabling a.
So this
here we
is
go. Yeah,
this is the timeline. This is the things that run. I mean, that doesn't necessarily correspond to the previous execution, but maybe one I did a few days ago. This is the timeline, including the time it took and the memory used. And this is the what's it called? Graph. DAG. Flowchart. This is the flowchart. So this is the actual DAG. The one that I promised I'll show you a better version of. Here it is. So if you want to, you can see channels. You can see the processes here. You can see what operators I use, mix in this case. You can see that I use a from path. You can see how they are all connected together to produce the final output, which we can go into a lot of detail on. It will take a bit longer. So that is it from me. My suggestion is to use it. And if what you saw did not inspire you and motivate you to, a witty quote here will also fail. So thank you very much.
Thanks, Costa. I have one last slide to show you as well. I forgot because I cut my last bit, but there's one important one.
Which will also remain in the recording. So that, and I'm also happy to share the slides with the attendees and anyone interested actually. And that's the. So here we go, just some further material. So in these slides, the first line is just the Git repo where my inputs for the demo were. But this is quite cool, the second one. So the Nextflow developers have released some materials to learn Nextflow, like literally 3 or 4 days worth of materials. We did the workshop with them in Perth just before the pandemic started, and they were worth like 3 days of hands-on. And they also have recordings for that on YouTube. So that's really quite cool. It's the 2 main developers, Paolo and Evan, that lead those. They developed the materials and recorded the sessions. And it's really high value for anyone that wants to get to know more and get started with Nextflow and write their own pipelines.
Cool. So
thank you.
Any other questions?
Are there any questions? Yes.
Or from individuals who are online?
So we can I think we can for anyone who has time we can take it into a question and discussion.
Yes,
we have time, and yeah, maybe hopefully we'll just if we can create more of a user community. So one of the things is that one of the motivations for this talk was that we didn't see anyone other bioinformatics community using it, and I thought, well, when I first saw it, I rejected it because of that reason. Then I saw it's really general purpose. It is really fantastic, and well, it's been extremely useful for me. I have so many good things to say about it. It's not perfect, but yeah, that was I think one of my main motivations to organize this.
Yeah, I think that's important to know.
Yeah.
If it's put with a domain, then you're not going to look at it.
Yep. Questions?
Yep. Harrison, go ahead, please, and unmute. You can ask.
Hey guys, thanks for the talk. Good to see you, Costa. I was reading through some of the Slurm docs just recently about how you can submit jobs to different clusters, and in the Pawsey docs that were mentioning Nextflow, and it was saying that you need to sort of create custom executor classes and then recompile Nextflow. I don't know if I was reading some old documentation there, but is that accurate?
Yeah, it was me. I wrote that. So okay. Yeah, unfortunately, Nextflow is not supporting multiple clusters in Slurm natively, and they're not interested right now in adding that. So yeah, it can be done by hacking the code, and so that's why I documented that, because it's even scriptable. I mean, it's a quite targeted hack in the source code. The main difference is that then you need to build Nextflow yourself, not just download the executable from the repo.
I did see that. I thought it was a shame that they didn't support it, but hopefully they add support for that sometime in the future, you know. Yeah,
and also, I mean, there are a few cases where you may need that. The other ones, say NCI in Canberra, they have quite a heavily customized PBS deployment. So you had to hack Nextflow there, because otherwise it wouldn't run at all on Gaudi. And I'm not an expert of PBS, but I get that some schedulers can be heavily customized compared to the standard typical deployments. And if that's the case, then you need to tweak a bit the way Nextflow interacts with them. But luckily, it's easy hacks on the
I've recently been going down the rabbit hole of sort of chaining together scripts in a similar way that Costa had originally, and I think I've got it to a point where it's okay, but I was looking at migrating some of my stuff to Nextflow, so there's a good chance I might be getting in touch with one of you guys to pick your brains at some point in the future.
Yeah, sure, but I think you're referring to are you referring to the Kotter workflow?
Yes, the Asvo Kotter workflow. I was sort of evaluating whether Nextflow would be a good fit for that, but
I wonder.
I wonder as well.
I think it's easier to keep it simple in this case, but let's take it offline.
Yeah, for sure. Thanks again, guys.
Thank you. And just as a full disclaimer, I also went to the same experience. I mean, my first pipeline for bioinformatics was in Bash, and it was a nightmare. So, I mean, I was very happy when I brought it, but then a month later, I had to write some variations of the same pipeline. I ended up with like tens of different bash scripts. And it was just a nightmare to even understand what it was doing a month later. So
one of the
that's how I started
is inflicting it on your colleagues
yes.
who are trying to run this. So I think
it has to be a black box if it's a bash script, right? You're like, sure, I'll press enter. It's very painful to look at.
Okay, any other questions online or in the room? Yes.
So
I will flip the screen for a second so you guys get
to
see.
Camera. You're not joined? Okay.
So we are really,
echoes.
it's a face-to-face.
So this is Pascal Elaki. I don't know if you can hear him. Yeah.
Hopefully you can hear me.
Yep.
I was going to say, what was, did you actually do a lot of tutorials and training before you started Nextflow, or did you start messing around with
It's
Nextflow?
really fast.
Yeah.
I mean, I don't know if I'm the typical case for it, because I also already have extensive experience for about, I don't know, 5, let's say, programming languages, and that fits very well with the way I think. But rapid prototyping is one thing. If you go through the tutorials, you will see you don't need to be an expert.
Yeah.
You can rapidly prototype something. The hello world that we saw, that's it. You can do something like that in no time. How much do you need to understand more than the keyboard?
Yeah. So I mean, I also found it's quite easy to think about, especially if you understand sort of roughly what the rough processes are in a more complicated pipeline. I think the main bottleneck is figuring out sort of that DAG, right? So that what is the graph of actual processes? Because once you have a sense of understanding of that, I find it's quite easy to generate prototypes.
Yeah, and hopefully we can by talking here we can if you come up with some bottleneck when you're using Nextflow, we can discuss, oh, you know, I did this, I did that way, I have this problem. I find I have this very annoying thing that I need to carry an argument, and I haven't found a good solution for it. I need to carry an argument between processes just so that the third process down the line uses it. But there is no good way to group. There is a grouping. There is a grouping. I know there is a grouping, but I needed to be very specific. But we can talk about this. I am interested in that. Yeah.
Yeah, I guess also like kind of forces you to document your input outputs quite early on in your development process, which is a good thing. Yeah.
As Pascal said, yeah, the language itself, and also Costa, is very expressive, which means it comes quite easy and almost fun to write these things. Actually, the DSL2 improvement on the language was quite crucial in that, because the previous version was very error prone. I used to make a lot of, I couldn't remember the exact syntaxes for many aspects of a pipeline. Now with DSL2, most of the points of possible error have been taken away. So it's really much easier to write a full pipeline in little time, which helps the experience. And as Costa said, it's about rapid prototyping, being able to test your pipeline quickly, and you can do that, and then you can scale it as quick as well, thanks to the way you can configure to different target machines.
Plumbing is taking care for you. Well, they are doing all that you've seen in all these scripts. They've done it for you, so you don't have to worry about, oh, how am I going to run this on Singularity?
Yeah, documentation is quite good. I mean,
documentation is fantastic. Yeah.
The community, I think they're not on Slack, they are on a thing that I didn't know called Gitter, which is very popular amongst video gamers, I think.
No,
or
just
no.
General.
Okay, but yeah, they are on Gitter. I don't go there often, but yeah, the documentation really gives you most of what you need. And say regarding Groovy, I did have to learn a couple of Groovy specific syntaxes, but really over 3 or 4 pipelines I wrote, it was really a minimal effort, because the language I developed that was specific to pipelines was quite powerful. So you almost never need to resort to low-level Groovy, which is not too bad. I mean, I don't know Java at all, but it's not too difficult to get a grasp.
If you have written 10 lines of either Java or Scala, or I don't know, any such thing, you immediately understand, oh, I can't do this in a script very well. Or in fact, some of these things you can do in a script. But in my case, I said, well, it's very easy to just pull a library for Groovy. And the cool thing, what I really like about Groovy, I didn't have to go into the build system and say package things and things like that. Just in the beginning, I said, just grab this using the Maven identifier, grab this. In this case, I was using Apache Commons library for JSON or for files, whatever it is, on the top, just grab it and then use it. 2 lines, and then I have my JSON libraries, I have my file system libraries, and that's it. There's nothing else. It's fantastic.